Welcome back everyone. After mastering how to build complete flexible classes with properties, operator overloading, and object formatting, today we are ready for the next major milestone in object-oriented programming: inheritance. Inheritance allows us to create relationships between classes, reuse code elegantly, and model the real world with even more precision. Inheritance will allow us to create class hierarchies, promote code reuse, and model real-world relationships even more naturally. From this point forward, you will start seeing software not just as isolated classes, but as a connected hierarchy of types, just like the real-world structures around us. Let's dive into it. Here's our learning path for today. Understand the meaning of inheritance, learn how to extend existing classes, handle access protection wisely, customize inherited behaviors, understand class relationships using ISA logic, see how UML diagrams can show these relationships clearly. We're building the foundation for larger, smarter systems, not just simple programs. Our main goal today is to think in terms of relationships between classes, not isolated classes. We'll practice how a child class borrows and customizes features from a parent class, access levels, protected private control, how children use their inheritance. Inheritance makes programs easier to expand and maintain in the future. The logic is simple: reuse what's already built and specialize only when needed. Inheritance allows us to avoid duplication and model real-world categories. For example, all animals have basic traits. If we code that once in a parent class, we don't need to rewrite it for every animal like dog, cat, or bird. Inheritance is about building a solid base once and extending it logically whenever needed. Inheritance always answers the question, is a derived class truly a type of the base class? A freshman is a student. A cat is an animal. If the answer is yes, inheritance makes sense. Good inheritance creates natural hierarchies. Bad inheritance creates confusion. Always think carefully about the ISA rule. In OOP, inheritance is how we organize related types and share common code. Base class defines common fields and behaviors. Derived class inherits these and adds or modifies special features. Think of a rectangle and a square. Both are quadrilaterals, 4 sides, but with different rules. Inheritance captures this natural structure in code. It's structure with purpose, not just recycling code. When you inherit a class, you automatically gain access to its public and protected members. You do not inherit private fields. They stay hidden to preserve security. Protected fields create a family-only access. Only the class itself and its descendants can see them. This careful control supports both reuse and safety. Here's how inheritance looks in different domains: geometry, quadrilateral give, rectangle, square. Vehicles, vehicle give, car, truck. Employment, employee give, faculty, staff. In each case, child classes inherit everything general and add their own specifics. Think logically. Only create a child class when it truly needs some extra specialization beyond the base class. Keywords to master: base class, the general parent class; derived class, the specialized child class. And importantly, inheritance is transitive. If A inherits B and B inherits C, then A inherits C too. This property builds layered knowledge inside your code. Smart designs flow naturally through multiple generations of classes. Alright, let's focus on one of the most important foundations in OP: designing good base classes. Purpose of a base class. A base class is a general blueprint. It defines the common attributes and behaviors that all child classes will inherit. Key guidelines. Generalization. Only include features that all future derived classes will logically share. Encapsulation. Make fields private if they should not be modified directly. Provide protected or public properties for controlled access. Why care? A clean base class means that your derived classes will be simpler. Maintenance will be easier. Fix in one place, improve everywhere. You'll avoid ugly, forced inheritance where subclasses have to deal with irrelevant fields or behaviors. Designing a good base class is like laying the foundation of a building. If it's weak or messy, everything above will suffer. To understand inheritance better, let's see it across different fields. 1. Students. Base class, student. Derived classes. Graduate student, undergraduate student. All students share basic features, name, ID, program, but graduate students have thesis topics. Undergraduates might have internship info. 2. Loans. Base class, loan. Derived classes, car loan, mortgage loan. All loans have principal, interest rate, and term. Specialized loans add vehicle information or property data. 3. Space objects. Base class, space object. Derived classes, star, planet, moon. All space objects have mass and position, but a star might have luminosity, a planet might orbit a star, and a moon orbits a planet. Key logic. Inheritance works when you can cleanly separate what is common and what is specialized. Now let's think about the bigger picture. Inheritance creates trees. Inheritance naturally organizes classes into a tree or hierarchy. Root node, the most general class. Branches, specializations. Why structure matters. It brings clarity. You know where each functionality belongs. It brings scalability. Adding new types becomes easy without rewriting old code. It mirrors real-world organization, companies, ecosystems, libraries. Everything follows hierarchical structures. Good hierarchies keep software organized as it grows in complexity. Here's an excellent example in a university. Everyone belongs to community member. Then we specialize into employee, student, alumni. Employees specialize further into faculty and staff. In a UML diagram, this would be shown as a tree, boxes for each class, arrows showing who inherits from whom. This diagram isn't just documentation. It helps you plan and understand the logic of your system at a glance. Another classic example, the shape hierarchy. First root class, shape, base features, name, color, boundary properties. Second major categories, two-dimensional shape, flat shapes, circle, square, triangle. Three-dimensional shape, volumetric shapes, sphere, cube, pyramid. Third specialized classes, circle has a radius, square has side length, sphere has volume calculation based on radius. Now UML representation diagram, one root shape box, two branches, 2D and 3D, sub-branches for each specific shape. Finally, let's conclude what we've learned so far. Inheritance lets you reuse code, organize your types, and mirror real-world structures. You must think carefully about what goes into a base class, only what is truly common. Specialized behavior belongs in derived classes. Not everything should live in the parent. Hierarchies bring clarity and scalability to big systems. UML diagrams help you plan and communicate your class structures clearly before you even start coding. Inheritance is not just a syntax trick. It's a powerful thinking tool that, when used correctly, will make your programs easier to build, easier to grow, and easier to maintain. In the next sections, we'll move from theory into practice, writing inheritance syntax, using protected members, overriding methods properly, and building deeper, more flexible class trees. Keep the logic of clean structure and real-world modeling always in your mind. It's the key to becoming a great object-oriented programmer.